Thank you all for coming in. Thank you, Alex, for coming to give us a talk. I think almost everyone here knows who Alex is and is excited to hear him talk, but nevertheless, I will do an introduction. Alex is an associate researcher at the University of Gothenburg, and he does primarily interdisciplinary research in computational linguistics with an emphasis on learning theory and language acquisition, which he's going to talk to us about today, partially, mostly about context-free grammars and tree-adjacent grammars. So I'm glad to hear what you have to tell us.
Great.
Thank you.
Yeah, so thanks for the invitation. I think it's a really nice environment to have these seminars. And so I'd kind of like to exploit that by encouraging you to ask questions during the thing rather than having like a formal me talking for a bit and then having a Q&A at the end. I think it's more interesting just to just start. And since it's a small group, don't worry about sticking your hand up, just start shouting. Okay, so yeah, so I'm going to talk about learning probabilistic context-free grammars and tree adjoining grammars and multiple context-free grammars. And I could talk about each of these at length. They're basically, it's kind of the same idea in all three of these. And it works for quite a large class of grammars that have a sort of underlying context-free backbone, right? So if you have some sort of grammar which has some sort of underlying derivation tree, and then from that you produce strings, or you produce trees, or you produce tuples of strings or whatever, then it's basically the same idea. So I'll spend most of my time on the PCFG bit, which has the kind of shared idea. And then I'll talk about the extensions to tree adjoining grammars and MCFGs. And I was a bit lazy, and so these obviously the slides I used for another purpose, and they were directed towards a linguistic audience. So there's going to be some stuff which is kind of linguist facing, which I'll kind of skip over a little bit. But I mean, if you want to talk about it, but I'll just sort of trot through that stuff fairly quickly to get to the kind of technical material. So algorithms for learning probabilistic context-free grammars. And I think kind of there aren't really any. I mean, if you think of an algorithm as being something where, it's guaranteed to produce the right answer, then there really aren't any good algorithms for learning probabilistic context-free grammars. So sure, you can compute the gradient, you can use gradient descent, and you can use the EM, and they have some theoretical guarantees. But those guarantees are just to kind of converge to some grammar, that has a higher, likelihood than some adjacent grammars. It's just a local maximum of a thing. So it doesn't really tell you anything about what you're going to learn, what grammars you can learn, what grammar is going to converge to, how likely it's to converge to that grammar, or anything else. So that's kind of, I mean, it's just like a huge gap in, it's a huge technical gap, which I've been trying to fill for a number of years. And the scientific question is about the acquisition of syntactic structure. So in first language acquisition, children are exposed to a bunch of strings from the language and some other information, and they acquire syntactic structure. And so I think everybody agrees you need syntactic structure. Whether it looks like the syntactic structure that linguists hypothesize is a different question, but you need some structure, and maybe that's something that looks radically different from a tree, but I'm going to stick quite closely to kind of the sorts of structures that linguists hypothesize. And there are some big kind of picture questions about, theoretical linguistics, which I'll kind of skip over. What we mean language is like a set of four meaning pairs. Better think of it as a probability distribution, where S is a string of some sort of acoustic categories, or we're going to think of them as words, and M is some semantic representation. And so if you come from a machine learning background, then it's kind of fairly standard to think about having some latent variable and some sort of joint model that unmints it. And we have a couple of probabilistic mappings to the strings and things, and then we sum over this latent model. And this is kind of very close to a sort of a standard model that is used in linguistics. So there's this kind of really old diagram from Chomsky, I know 65 or something, where he just talks about, the language acquisition device as being a function from the data the child is exposed to the child. And everybody laughs about this and mocks it because it's so ludicrously idealized because the child does lots of other stuff. But I think it's entirely legitimate, right? You idealize the scientific problem, and then, what are the simple models that result as a result of that idealization? It's like with comprehension, where you have some mapping from a string to a tree. You're using this to model the process of language understanding. And obviously there's lots of other stuff going on, but you have a theory of parsing, and that theory of parsing can be hooked up with psycholinguistic work. Milos has done some work on this, and it's kind of like, you idealize, but then you get some result from that idealization. And so if you're thinking about language acquisition, what are the idealized, the simple models that you have for learning probabilistic context-free grammars and other things? And so how are we going to model this, right? So one assumption that people use, which I think is widely adopted but kind of inappropriate, is that the input are form meaning pairs. So the input then would be a sequence of words and then some semantic annotations of those words, semantic annotations of those sentences. So it would be like some sentence, John likes cats or whatever, and then you'd have another thing which represents the meaning of that. And then the output, then you want to converge it to having some sort of approximate probabilistic matching between these probability distributions. But actually, I'll speed up on this because I think it's a bit, but we don't observe the meanings. That's a basic problem. I mean, the child doesn't know what the sentences means when they're learning, right? And then the second thing to do is just think about, ignore the semantics for the moment and just try to generate the right distribution over strings, okay? So you have a sequence of strings as input, sampled from the distribution of the child, as it were. And then we just want the child to learn some grammar or some model that generates the same distribution over strings. We don't care about the representation, we don't care about the meanings, we just want to get the strings right. And this is kind of just language modeling, which is what everybody does, right? And I mean, it's kind of too weak because here you're just requiring to get the right distribution over strings. But it's also not that weak because actually, in order to get the probability distribution of strings right, you've got to have some sort of representations, and those representations turn out to be pretty close to what linguists hypothesize, right? So buried deep inside your transformed language model, there are layers which have implicit hierarchical structure. Okay, so it doesn't look like the sort of things that a linguist would hypothesize, but there is some structure there, and it turns out that structure do the right thing. But I'm not talking about that. I want some kind of strong learning here, and so this is the kind of the tough learning model which I'm interested in, which is you ignore the semantics, right? But you're trying to generate the right distribution over strings, but also over unobserved trees, right? So we're trying to recover not just the right distribution over strings, but also the right distribution over the unobserved latent trees, right? Now, obviously, since you don't observe the trees, you can't hope to get exactly the labels right, okay? But you can hope to have the labels up to some relabeling, up to some sort of isomorphism. And this is a problem that's been around for a while. It's called, like in the NLP literature, it's like unsupervised parsing, grammar reduction, whatever. And it's kind of plausible. The inputs are plausible, the outputs are kind of interesting, plausible. The problem is it's like really, really hard. So roadmap here, I'm going to talk about this, solving this problem in for context-free grammars in Chomsky normal form. I'll talk about tree adjoining grammars from learning tree adjoining grammars from derived trees. I'll talk about very briefly about learning well-nested MCFGs from strings, but I won't talk about another paper which is about removing the CNF restriction. So I wrote all these, I worked a long time on this paper, which I published with Nathaniel Fijalkow. So I spent several years on that, and then I sort of wrote these follow-up papers quite rapidly. I didn't realize that they would all be kind of straightforward to write, so that's why I wrote them separately rather than just writing one long one. Okay, so let's just start with like context-free grammars. Just refresh, everybody knows this, but you have a context-free grammar in Chomsky normal form. You've got two sorts of productions. So here I'm using the convention that capital letters are non-terminals and lowercase letters are words or terminal symbols. So think of them as being words or the exponents of words. And so we get little trees like this. And we can take this tree and can split it into two parts. So one is like a derivation context and one is a derivation like little subtree. And it's helpful to like, instead of writing it, sorry, instead of writing this form where the labels are non-terminals, it's kind of more convenient to write it where the labels are productions, okay? So the labels of the derivation tree are productions. And so we can split a derivation tree here into a derivation context and a derivation subtree here. And we're going to use, this is pretty much the only kind of non-standard notation here, but omega is a set of all trees with A at the root, and chi of A is the set of all contexts of A with S at the root. So here what we got is we've got an element of chi of A and an element of omega of A, and we stick them together to get a whole tree, okay? So you can think of this derivation tree here as being a function, and this little gap here as being a variable, okay? And it's a function that takes this thing to a whole tree.
Could I, just to clarify,
yeah,
omega of A is the left one or the right one?
The right one. So this is a set of all trees with A, oh, I should put the D maybe. Okay, so yeah, this is the omega D here, and this is a chi of D. So chi is the context as well.
I see.
That's the heuristic.
Thanks.
Okay, so we're going to be working with probabilistic context-free grammars. It's better to look, I think, at them as a special case of weighted context-free grammars. So we have a parameter theta for each production, which is just a real number. And then we define the weight of a tree as just being, the weight of a tree, tau, as being just the product over all these parameters, over all the productions pi, the parameter of pi, plus time to the raised to the power of the number of times we have pi occurs in that tree tau. So it's just kind of standard log linear model, okay? And then we define here, so the weight of a set of trees is just the sum of the weight of all the trees. So given this here, we can define for each non-terminal two quantities, which is kind of the inside and outside quantities here. So the inside score here is the weight of all of the yields of the thing. And the outside is the weight of all the contexts, okay? So it's just, you just sum up you sum the weights over all the possible contexts and all the possible things, you get these two quantities, okay? And now we want a probability distribution, okay? So we're going to stipulate that the inside score of the start symbol is 1. That just means the sum of the probabilities, the sum of the weights of all of the trees generated by the start symbol is equal to 1. So that gives us a nice probability distribution over these trees. So
wait, can I ask you a quick question?
Yeah.
Could you go back a slide? So is this so this is inside and outside probabilities over the entire grammar, not for a particular tree?
Yeah, so it's exactly, so it's a sum over the inside. And it's also not, we're dealing with a weighted context-free grammar, not a probabilistic context-free grammar at this point, okay? So these are just, I'm using I and they just kind of get, yes, they're close, these are very close related to the inside and outside probabilities of the inside-outside algorithm, okay? Okay. So it's, you know, if you think this is just sum over all the yields, sum over all contexts, but, and then we'll come to that. But yeah, exactly, that's the connection. Now, I say it's a trivial identity for W. I mean, it's kind of one of those identities that's really, really trivial, like once you've kind of thought about it for a little bit. But basically, if you, for any, if you have a probability distribution, right? For any non-terminal, the product of the inside and the outside scores is going to be equal to the expected number of times you see that in a random tree, okay? And that's kind of because if you just think of it as, if you have the sum of each tree and you split it each thing and then you reorder the sum, on one thing you have the score of each tree times the number of times it is, and on the other hand, you reorganize it and you sum it over the inside and the outside things, okay? So it's trivial. It's such a kind of, sorry, I apologize for saying trivial, an interesting and non-trivial identity, okay? But anyway, this turns out to be pretty true. If you sort of think about what it is as sum, it kind of makes sense, okay? And there's sort of, if you have this here, the other thing to recognize with these weighted things is you can kind of fiddle around the parameters a little bit, okay? With these weighted, with these weights, here you can kind of scale the weights a little bit and get, they're kind of, they're sort of a little bit arbitrary here. And so you have some choice over what you do. And so one of the things you can do is stipulate that for every, sorry, wrong one. You stipulate that the inside score for each non-terminal is equal to 1, okay? And then, so obviously the outside score has to be expectation, okay? And then the parameters are going to satisfy these two parameters, these two equations here, right? And this is just a PCFG, right? So the parameter associated to A goes to BC. It's just the expected number of times you see that production divided by expected number of times you see the left-hand side. So this is conditional on the left-hand side. And these parameters then have this nice interpretation as a conditional probability in a top-down geometric process starting with S, okay? So this is what everybody uses for probability distributions over context-free grammars, okay? We're not going to do that. We need something different, okay? So we're going to do it the other way around. We're going to stipulate that the outside score is equal to 1, okay? And the inside score is going to be equal to the expectation, okay? So in this case, each non-terminal then defines a probability distribution over its contexts rather than the probability distribution over its yields, okay? And then the parameters are no longer conditional probabilities, but they satisfy this kind of, these identities here. So you can see they're being kind of normalized by the non-terminals on the right-hand side rather than the left-hand side, okay? Why do you want to do this? Yes, go ahead.
So if you're doing this over the whole grammar, but you're showing that, so these parameter equations, like they look like the EM update equations, but if you just do this over a whole grammar, does it actually cause an EM update?
So yeah, so when you so when you're doing an EM update, right, you count the expectations, right, and then you normalize them to get a PCFG, okay? You can do the same thing, do the expectations and then normalize the other side, and then you'll get this sort of thing, okay? I think the thing is, like, when you're thinking about these things, thinking in terms of expectations rather than probabilities is the right thing to do, okay? So you have your tree, right? Maybe you've got a tree bank, right? Okay, you can just count the number of things. You can count the number of things. This will give the expected number of times you do things, and then you can normalize them to get these conditional probabilities, okay? The expectation of the fundamental properties, if you're given a distribution over strings, distribution over trees, then that gives you these expectations. Then you need to decide how you're going to parameterize it. And there are these two different kind of equivalent ways of parameterizing. You can convert from one to the other. You need to like solve some equations numerically, but it's doable. Okay, I mean, it's kind of straightforward. Okay. So this is, so going to the PCFG thing right here, this equation here is actually really interesting. I mean, it's kind of obvious, but I'll discuss it briefly here. So on the left-hand side of this equation, you have a parameter of the grammar, right? On the right-hand side of the equation, you have something which depends only on the distribution of trees, okay? So that means if you're given the distribution over trees, we can just like write down the parameters, okay? So this is like tree bank, maximum likelihood estimation of a tree bank parser, basically. which doesn't work very well, but theoretically it works fine. So we can't have two PCFGs that generate the same distribution over trees. So this gives a recipe to learn the parameters. Then we just like count the tree. If we observe the trees, it's easy. We just count them and normalize them, and we're done, right? So learning PCFGs from trees in the observed setting is kind of, I wouldn't say trivial, but it's straightforward.
Does a tree include the non-terminal?
Mm-hmm.
Does a tree?
Yeah. So a labeled tree. I'm talking always about labeled trees. Yeah, good question. So this is great, right? If we see the trees, but what if we just see the strings, which is the case we're interested in? Okay, and obviously, if we see if we only see the strings, PCFGs are not identifiable, right? Because you can have two PCFGs that generate the same distribution over strings, but generate completely different distributions over trees, right? So suppose we have a distribution over strings, which just assigns probability 1 to this string of length 3, ABC, right? We could have a PCFG that looks like this first one, or a PCFG that looks like the second one. There's no way we can tell which one of these two they are, right? So the trees are not identifiable in general from the strings. So like everything I'm trying to do kind of doesn't work, okay? But let's ask it actually. Okay, so obviously we need to have some sort of restriction on this. So we can't hope to do this for all PCFGs. We can only hope to do it for some PCFGs. So I'm going to use a technique called distributional learning. So this is very kind of linguist-centric here. But so basically the idea is here you've got this, you have sentences like this. I'm thinking about child-directed speech, whatever. We just have the idea that this word kitten occurs in these contexts. The blank is over there. Oh. So I made, this is a mistake I made when I gave this talk before, and I didn't correct the typo immediately. So this final line here, it's what acute square is the context, because this is not. So, but the word dog does occur in these contexts, right? And so this is the basic idea of distributional learning, is that a particular word defines a distribution over its contexts. Okay, so suppose we're given a probability distribution over strings of symbols, right? A string, which could be a particular word or a sequence of words, defines a probability distribution over its context. And I'll use a bold U here to represent this vector. So it's just a distributional vector, okay? Where the L blank R, L gap R, has probability proportional to the probability value R. And the expectation here is just a normalization constant, right? When you sum over all these things, you're going to get 1. And again, we see an expectation cropping up. Again, this is like, I mean, the thing is, working with these expectations, eventually they're all going to cancel out and it'll be really nice, but we're not quite there. So each word, each string or sequence of, each word or sequence of words defines this probability distribution over its contexts.
Could I actually grab you on the previous slide?
Yeah.
How did we do really this relation between probability and expectation? That's something.
So think about a particular, suppose U is just a single word, right? Okay, mm-hmm. Kitten, say, okay. Mm-hmm. So we want to have we have a vector where each distribution, like the gap is over there, has probability proportional to the probability of the kitten is over there, okay? Right? Then when we sum up over all of those contexts, we're going to get something which is the expected number of times the word kitten occurs in a random sentence, which is just the unigram probability multiplied by the expected length of the sentence, right? So it's basically, the expectation is basically unigram probability, but it's multiplied by the expected length because we're considering whole sentences rather than individual words.
So we're going to get the probability of LUR given U.
Yes, exactly.
But in a specific sentence, in a sort of relative to the length of the sentence.
Exactly. So pick, you have a consider infinite corpus, you pick some particular occurrence of a particular token of kitten, and then say, what is the probability that the rest of the sentence is this? Okay.
Okay.
So I'm using this a term called anchored context-free grammars, which follows this nice paper by Carl Stratos, which is about anchored hidden Markov models. And we're going to assume here, and this is the kind of the major assumption, right, that for every non-terminal, there's a terminal, so there's a word which occurs only in that production. Okay, so we assume there's, for every non-terminal, there's an unambiguous word that just comes from that. Okay, so a lot of words are ambiguous in English, but the word she, for example, is unambiguous. The word the is unambiguous, I think. The word kitten is unambiguous. Okay, so there are lots of unambiguous words. The question, we're saying that there are going to be enough unambiguous words that for every non-terminal there's an unambiguous word that's directly from that, only from that non-terminal. Okay, and it's kind of a reasonable assumption if on two conditions. First is that the number of words is much greater than the number of non-terminals, obviously. And the second is the grammar is not excessively ambiguous, right? That it can be ambiguous, but it can't be insanely ambiguous. So then the idea is here, we put all this together, like say you have strings like she and the kitten. So she is some noun phrase, the is a determinant, kitten is noun. So the idea is that looking at the distributional properties of these two strings, she and the kitten, should tell you something about the production. Noun phrase goes to determinant noun, okay? And they're two very old ideas. One is that the kitten should occur together more frequently than we expect by chance. Okay, and the second idea is that she and the kitten should be distributionally similar. They should occur, their distributional vectors should be similar to each other. So to measure distributional similarity, we need to use we need to use a Renyi divergence, which is a generalization of the Kullback-Leibler divergence. And in this particular case, we want to use this, there's a kind of hyperparameter alpha, and we need this version which has alpha equals infinity. And this is just the supremum in log space of the ratio of the probabilities of these two things, okay? So in this context, the distributional, suppose you have the vector of, suppose you have a word, you know, say cat and dog, right? What's the largest change in probability when you replace cat with dog, okay? But where you adjust for the relative frequency of the two things, okay? So if we replace cat with dog, that could decrease the probability a lot, okay? If it decreases it a large amount, then they're going to have a large distance. We take the maximum, the worst case of this. So this isn't a true distance, it's a divergence, but it's kind of quite well behaved as divergences go. There are two other conditions here. I'll kind of skip over these. So these are two technical conditions which basically say the grammar is kind of well behaved. So one is local unambiguity, which is a weak condition limiting how ambiguous the grammar is. And approximation of this is just think, so does every production occur in an unambiguous string? It's a bit weaker than this condition, but just, so there are some unambiguous sentences or sufficiently unambiguous sentences. So this is the kind of the main, so this slide I think is the one slide you should pay particular attention to. I mean, I'm sure you're all paying attention throughout, but just like, you know, this is the crucial slide. Okay, so under these conditions, right? This anchoring condition, given non-terminals, big A, big B, and big C, which are anchored by A, B, and C respectively, okay? The log of the bottom-up parameter, okay, is going to be equal to the sum of two terms. Hang on. So the first term here is basically the pointwise mutual information of the right-hand side of the production. Okay, so B and C here are words. Okay, so the kitten, to go back to the example here. So this is basically the pointwise mutual information of the kitten. Okay, there's a little normalization factor because we're not dealing with unigram probabilities, but with these expectations. And the second term is the minus the divergence of the left-hand side from the right-hand side. So the bold here, these are the vectors, okay? These are the distribution vectors. So this is how far away the distribution of the right-hand side, the kitten, is from the distribution of the left-hand side, which was they or she, I can't remember what it was, she, okay? So if we look at this again, right, the key thing here is that, like before, the right-hand side depends only on the distribution over strings, okay? So we have on the left-hand side, the parameter of the grammar. On the right-hand side, we have this term here, which just depends only on the distribution over strings, not on the distribution over trees. So obviously, this term on the right-hand side is not as nice and easy as the one we had on the expectation of trees, right? The expectation of trees we just counted and normalized, and it would be fine. This actually requires to do a little bit of non-trivial work. The first term here is obviously very easy to estimate, right? We just can estimate these things just essentially by counting and dividing. This is quite hard to estimate. In the worst case, it's extremely hard. But one can do it, right? It's if you can, I mean, you need to estimate this from sparse data, but that's kind of what NLP people know how to do, right? Are there any questions on this? Because this is like.
Could you explain in high level the meaning of the left-hand side?
So the left-hand side is the bottom-up parameter, okay? So so I think if you think about a normal, if you think about a PCFG, right? The normal top-down thing, right? That depends crucially on the expected number of times that the left-hand side the non-term of the left-hand side occurs, right? Which you don't know. So you can't really tell anything about the top-down parameter from distribution analysis, right?
Maybe I should, the A with the left arrow.
Yeah, so this, I put this, this is just to remind you that it's a bottom-up parameter rather than a top-down parameter, okay? So this is a CFG production, but yeah, so I have this slight bugbear. I will think that like, I will think that the arrow in a context-free grammar points in the wrong direction. So I will think it should be, you should write context-free grammars always with the productions this way, but I mean, I've yet to convince anybody that's a good idea. But anyway, I put it here just to kind of, just to highlight that it's a bottom-up parameter. So it's conditional.
Okay.
Yeah, Marco, you have a question. Just.
Yeah, I just want to make sure the second term, like the first term on the right side, to be clear, so I get what the denominator would be, but the top one, that's B and C occurring like in the same sentence, or literally B and C occurring directly next to each other, or B and C, and if it's just that they occur in this, actually in either case, they have to have occurred coming from non-terminals B and C, or they could have come from
Okay,
anything.
so good, yeah, so that's great, really good question. So okay, so they have to be adjacent, right? So it's the expected number of times that you would see a particular pair of words, a bigram, right, in your data. Okay, so this is bigram things, okay? Do they have to come from the non-terminals B and C? Well, yeah, because these are, we're assuming these ones are anchored, right? These are anchors. So we know that B can only come from a capital B, right? So that's a crucial, because of the anchoring assumption, right? We know the distribution of the word B is going to be essentially exactly equal to the distribution of the non-terminal B. And so that assumption means that we can make inferences about the productions, right, by just looking at the distribution of the yields of the things. So,
Okay, got it. Thanks.
Milos.
Yeah, yeah, my question is, how should we interpret the anchoring of A? So it's intuitive if it is a pre-terminal symbol,
Yep.
but if it is inside of the tree, is that the word that is most representative of that type of a constituent, or is it a kind of like a head-driven parsing where it's either one of the it's a head of one of the children, or I'm guessing it's a former one.
Yeah, so that's interesting. I mean, so in NLP, right, you tend to have this division of non-terminals into kind of pre-terminals and sort of internal terminals. So all the non-terminal symbols are, all the terminal symbols are introduced by these pre-terminals. So I'm not making that assumption here. So here we don't have this pre-terminal pre-terminal kind of non-pre-terminal distinction, okay? The issue is kind of on one circumstances, these grammars then fail to have the anchoring property. So, I mean, there are two ways that this can go wrong. One is that the non-terminal doesn't generate any strings of length 1, right? So, if, for example, I have a little corpus study later on. Actually, maybe I'll just scoop ahead to that actually, since it's relevant here. So the anchoring assumption, right? So there are two ways that non-terminal would have no anchors, right? One is it doesn't generate any strings of length 1 at all, right? Okay, and the other is that all the strings it generates are highly ambiguous. Okay, so I looked at a syntactically annotated corpus of English child-directed speech. Okay, and so here we have, these are sort of, they're using a kind of pen tree bank type annotation. Okay, so for each of the kind of categories here, what are the probability that the length generated by that thing is going to be equal to 1? Okay, so this is child-directed speech, so the statistical properties are very different from like a tree bank corpus where the sentences are much longer. Okay, so we can see that in quite a lot of the cases, it's sort of reasonable, right? And then there are several cases where it's completely fails, right? So in particular, when we have sentential complements, right? So here, these S things, right? Basically 0 of the, they basically don't generate a very large number of, there just aren't single sentences clauses in the corpus, right? So there are some clauses some categories where the anchoring assumption won't work because we need to have anchors that are of length greater than 1, basically. And this approach is just assuming we have an anchor of length just 1. And then the other case where it doesn't work is, yeah, so, and then here I've got what's the best anchor of amongst ones that have occur reasonably frequently. What's the best anchor and what's the probability that it is an anchor? So, so the other failure here is the prepositional phrase, which prepositional phrases in English always have at least 2 words, basically. And so this is, I don't know where that comes from. But again, I don't really believe in prepositional phrases because I think distribution, they count as adjuncts. So, so I think it's, but what this shows really is that the anchoring assumption is, as I'm dealing with here, is inadequate, and you need to extend it so it can cope with anchors of length greater than 1. If you have anchors of length greater than 1, if you can identify the anchors, then let me just go. Yeah, if you can identify anchors of length greater than 1, then this works fine. If you go through the maths, this identity is exactly the same. The problem is just identifying what the anchors are. And there do seem to be anchors for like clausal categories of length greater than 1. But it's a little difficult to formalize the intuition of doing that. Yeah, and then, yeah, so that's the other sort of rule that we have in this is this lexical rule. And for the parameter here, it's the kind of same sort of thing, but it's even simpler. So the bottom-up parameter here is just the lexical frequency of the right-hand of the word and the divergence of the left-hand side from the right-hand side. Yeah, so this is kind of a bit of a waffle about why we need to do bottom. I mean, the real reason you need to use a bottom-up parameter is because the maths works out. But the intuition is you can't really tell what proportion of NPs are the kitten because you need to know how many noun phrases there are. And you don't know that. But it can tell you what proportion of occurrences of the kitten are noun phrases. So you kind of want to condition it on the right-hand side, not the left. And also it's kind of close to what you observe rather than what you don't observe. These are both kind of hand wavy. I mean, the real reason is just that the maths works out. Then identifying the terminals is just basically the context distribution of all the terminals lie in the convex hull of the anchors. So in distributional space here, you can just, if you can estimate these divergences, you can find the extremal points. You pick one of each of these, and that's your terminals. And so then you get a theorem. We can show that using a very naive estimator for these things, you can show that for all PCFGs here, if the underlying CFG is in Chomsky normal form, is anchored and satisfies these two additional conditions, then this will converge to a grammar which is isomorphic to the target grammar. So it will recover in the limit, and not, I mean, asymptotically, it will recover exactly the right distribution over strings and exactly the right distribution over trees up to a relabeling of the non-terminals because you don't observe the labels. And I think I just think it's really weird. I mean, I've been working on learning context-free grammars for a while, and it's just, I think, really weird that there aren't any, like, why there aren't lots of other. I mean, it's just like feels really, really late. This is a result I feel that people should have had like 10 years ago. Hi, Satwick. Yeah.
Yeah, can you just go to the previous slide? I think I missed.
Yeah, sure.
Yeah, so here, so what does the computationally efficient thing exactly mean? Like, is it efficient in, like, in terms of which parameters or like?
Oh, so, yeah. So I think linear in the data size. So it's one of these algorithms where there's often a trade-off between the sample complexity and computational complexity. And this uses a very, very trivial algorithm where basically you're to estimate the, so to estimate these divergences, you don't do any real statistical estimation. You just like count up the whole sentences and wait for it to converge. You need to do that in a sort of not completely.
Do you like count and find the mean and use Chernoff to show polynomial number of, like you can do it with polynomial number?
No. So it's definitely not polynomial. So the convergence is very, very slow. The computational complexity is very, very low, though. I think computing this term is just counting and dividing, right? Computing this is basically, again, it's counting and dividing, but you need to count a lot of things. So the proof doesn't make any additional assumptions doesn't make any additional regularity conditions about the grammar, right? And in the worst case, estimating these things is extremely hard, right? Okay. So the trivial estimator converges very, very slowly. It's completely unrealistic. I had some computational work which kind of uses a less trivial estimator, which converges rapidly. But so that's where you trade off a little bit of computation for faster sample complexity. Yeah, so this is I put this in red because slow to converge just means like insanely slow. It's not, these aren't a practical algorithm. This is an algorithm which is easy to prove things about, but not practical.
One second. So what does identifiability exactly mean here? Like, so what is the setup? Like, suppose the algorithm, it takes like a lot of data,
yep.
And then does it give you like this PCFG, which is like somewhat close to the true PCFG, or is it exactly close when you have like a lot of data?
So the convergence here is just standard epsilon delta convergence, right? So what it says, what the theorem says is that for every grammar, for every epsilon, for every delta, there is an n such that if you sample n strings from PCFG with probability greater than 1 minus delta, you will get a PCFG which is isomorphic to the target data and where all the parameters are within epsilon of the true values. Okay.
Okay, and this n need not be polynomial. That is what you're saying. The number of this n, the number of samples, need not be polynomial. That is not polynomial.
That's not
rest
polynomial.
of the algorithm is
No.
efficient.
So it's quite hard to get polynomial results for, for regular things, even for the probabilistic regular things. And if you do prove anything about the things, you just end up with, like, there is some work on trying to get polynomial guarantees for a related algorithm. But it's very uninsightful. You have to stratify it by several different quantities. You end up with, like, there's lots of kind of very high powered things in that thing. So let me, I did want to talk about tags, actually. Can I also, there is some, okay. So there are some computation experiments, but I kind of don't want to talk about this. These are computation experiments where you're kind of using a small amount of data on synthetically generated examples. So each dot here is a grammar, a synthetically generated grammar. We're using unlabeled F1. And then these are various baselines. A, B, and C are the algorithm with varying amounts of EM. So this is the kind of a pure version of it. And then the ML and gold are the kind of gold standard things. So in practice, this is from a fairly small amount of data. This is from, I think, 1 million sentences or something. Let me talk about tree adjoining grammars. Context-free grammars are inadequate for natural language, right? And so I'm going to talk about learning tree adjoining grammars, which they have a more powerful grammar formalism that generates trees, and then the trees generate the strings. Okay, so what the strategy I'm having here is to kind of basically take combine a PCFG learner that learns basically learns the trees from strings, and then a tree grammar learner that learns the tree grammar from the trees. Okay, so the idea here is then that what is observed now is this a stochastic language of binary trees. Okay, so when we're learning with strings, what we observe is the strings, which is a sort of one-dimensional tree. And there we have a natural notion of kind of splitting a string into a word or sequence and its context. So in this case here, we can do the same sort of thing. So here we have G, this observed symbol G, which occurs in 2 places here. And so this has 2 contexts here. And so here, instead of having like a string with a gap in it, here we have a tree with a gap in it. So then in distributional learning from strings, here we have A and B, C, and we're saying they're going to, the left and right context is going to be similar. In distributional learning from trees here, we have some A, which suppose this occurs on the bottom of the tree, right? Then we might say that there's going to be this terminal A occurs in similar context to this little treelet here, B, C, D, okay? So when we're looking at strings, we just have a little chunk, a little bigram. Here we have the equivalent of a bigram in a tree, which actually has 3 bits because the smallest non-trivial tree has 3 things in it, okay? If you just look at the trees that occur on the end, at the bottom of the tree, then you just get regular tree grammars. What we're interested in is trees that occur in the things also in the middle of the tree. So like the G example here. So the idea is that we can take some individual element in the tree and then compare that to some other treelet here. And I have like maybe yeah. So here's an example here. So this is like a WH movement, right? So you have some WH question in English, and you can say something like, what do they like? And there's a tree where there's a little kind of E here, meaning a trace, which is where the what has moved out of. But you can also say, what do they think they like? Okay. And because we want to interpret the what as the object of like here, we need some grammar formalism where we get a kind of extended domain of locality, where at the derivational level, the what and the like are close to each other so that they can be interpreted. So that's the kind of the function of the thing. So what we can see here is that if we look at, oh, here, it did work, okay. So what we can see here is if we look at this node I boxed here, S, this occurs in a particular context here, which is actually exactly the same as the context of this larger chunk here. So the basic idea is that given the given these trees, we can do the same thing that we did with context-free grammars and strings and have these context-free tree grammars to generalize this here. So that means we would hypothesize, in this case, there's some sort of production that relates the non-terminal, that relates the non-term that corresponds to this observed symbol here to this chunk here. So this then would allow us to infer some sort of tree adjoining grammar type thing. So we're using these context-free tree grammars, which are called footed simple tree grammars. Okay, so here we have productions that are going to look like this, that are like context-free productions, but they're generating, the derived objects then are binary trees rather than strings. And so what this production here means is that it's a recipe for combining the trees together. So it says context-free production says, BC says we take a string and another string, we concatenate them together. This says we take 3 trees and stick them together. So we take these 3 trees together here, we glue them together to get this bigger tree here. So it's a set of instructions for building a tree, in just the same way that a context-free derivation is a set of instructions for building a string. And so we can get a CNF-style normal form for binary trees, where we have one set of productions here for the things that happen at the edge of the tree, at the bottom of the tree, which kind of looks like we don't have children, and another for the things that occur higher up in the tree, which do. And so then you have this 2-level thing here. So we have a derivation tree, which is then going to be ternary, right? Because each production has 3 non-terms on the right-hand side, which gives a derived tree, which is binary, which gives a string, which is unary, right? So the idea is then that using these learning mechanisms, we can invert this process. Given a bunch of strings, we can infer these trees, and then given a bunch of these trees, we can infer this. And so the crucial point here is that this is an example which has these sort of cross-serial dependencies, okay? So in the string here, we have A and A, right? In the derived tree, these A and A are far apart from each other. But in the derivation tree, these are local, these are close to each other. So here we have A and here we have B and B. They're both local with respect to derivation tree, but they give rise to cross-serial dependencies in the derived tree, in the string, okay? So this allows you to model the kind of non-context-free things. You get these unbounded number of cross-serial dependencies, which motivated the rejection of context-free grammars. in the late 80s. So tags as a formalism have a few kind of slightly differ from the sort of formalism I'm using. So first of all, tags use quite big right-hand sides normally. And so it's easy to kind of extend the normal form to trees of larger size. And tags typically don't have non-terminals, right? They use a slightly different sort of infrastructure, but basically they don't have the terminal non-terminal distinction that we have in a context-free grammar. That's kind of compatible with the anchoring assumption, because in a tree adjoining grammar, effectively the non-terminals and terminals are the same, just like in an anchored grammar. And then tags have this syntactic restriction where you kind of assume that the foot label equals you have productions which, let me just go back up to it. So here, if you look at this subtree here, we're replacing an S here with a subtree which has S at the root and an S at the foot, which is this one immediately above these things here. So that's kind of quite a strong syntactic constriction on the things, which we don't use in this formalism. But anyway, modulo these changes, you can use exactly the same algorithm that we use for learning PCFGs to learn this, these probabilistic tree adjoining grammars. So exactly the same conditions. We assume that each non-terminal then is anchored, locally unambiguous, and strictly upward monotonic. And then we can apply the same algorithm twice. So the first one is where you apply to strings to get some surface structure trees, and then you apply it to the trees. Okay, but there's a problem, right? I put these dots here because it's like there's that New Yorker cartoon about, like, at this point a miracle occurs, and there's definitely a miracle that needs to occur here to get from here to there, because these assumptions are a little bit kind of incompatible. But are there any questions about the tree adjoining grammar? This is probably going to be, if you haven't encountered tree adjoining grammars before, then this is probably going to be a little bit weird. But the basic idea is that, you know, you have these more abstract derivation trees that correspond to a deeper structure, that the same process that we use for inferring the trees from the strings can be used to infer these three-dimensional trees from the two-dimensional trees. No questions? Okay, so then this, I'll just talk briefly about, like, so this is kind of, I actually really like this idea about this two-step process, but kind of from a point of view of sort of mathematical and computational purity, it's not nice, because you have these two kind of incompatible algorithms, you know, just trying to glue them together. From a scientific point of view, I think it's, you know, it's unrealistic to try to model language acquisition through some kind of just a single process. You know, it's a multi-year process, and there's obviously several different things going on. So I think dividing into chunks and so on the chunks separate is fine. But from a point of view of mathematical purity, you kind of want to go directly from distribution over strings to a suitable structure. And so you can do that. Again, using exactly the same techniques with one small modification. So here we're using an extension of context-free grammars called multiple context-free grammars. And the main idea here is that we consider a context-free grammar to have two sorts of non-terminals. One is a non-terminal of dimension 1, which generates strings in the normal way. And the other is others are non-terminals of dimension 2, which generate pairs of strings, okay? We then need to use a slightly more different format for the sort of horn clause notation for the productions, because when we're dealing with these non-terminals that generate tuples of strings, there are several different ways to concatenate them. So we have a production here which goes A to A, and then we have these variables which specify how the various components of these right-hand side are combined together. And then when we do the distributional analysis, then we're going to split it not into a context and a yield. We have a context with which is kind of a string with two gaps, and the yield is going to be a pair of strings, and we put the first string in this one, the first string, the first gap, and the second string, the second gap to get this A, B, B. Okay, so this is a derivation tree for the string A, B, B that we split into two. So this notation here just says A generates a little a and a little b. We have two of those. This production says we combine them in a particular way to get two tuples, which are what I did. This is so A and B, and then we stick them together. So when we learn these sorts of things, you're going to look at distributions of pairs of strings. So you're going to have a tuple like which book and read and which cake eat. And these are going to occur in similar contexts, like which book did you read yesterday and which cake did you eat yesterday. And the idea is then is that from the distributional analysis of these things, we can infer directly a probabilistic multiple context free grammar. So to get this to work, you need to make a kind of implausible assumption, which is that every non-terminal A of dimension 2, you have distinct terminals A and B, such that A of A, B is the only production in the grammar using A or B. And so this is kind of fine if, in the case of context-free grammars, I think it's a reasonable assumption. For multiple context-free grammars, I think this is not a reasonable assumption. And I'm kind of thinking about how to do it, how to improve this, but that's the assumption we need at this point. And then the problem is really that if you have more than one occurrence of A and B, then you don't know which bit of A and which bit of B, which A's and B's go together, right? So suppose you have a derivation tree like this, okay? We've got A, B, and A, B here. Right? We've got two A's and two B's, right? But the distribution of A and B could involve one A from the observed string distribution, could involve one A from here and the B from here, okay? And so that will give you a string context which doesn't correspond to a derivation context of the non-terminal. So you need to have a restriction on the rules called this well-nestedness, which means that the non-terminals can't sort of interleave the tuples in a particular way. And this is actually this is actually a very interesting restriction, formal restriction on these mildly context-sensitive formalisms, because I'll just so well-nestedness has like that. I mean, it's a kind of very active area that Milos, I think, has worked on as well, which is that the well-nestedness condition. It says that these productions can be binarized, which gives you more efficient parsers. It excludes various excessive free word order languages. And some corpus studies suggest it generally holds as well in natural language corpora. And the well-nested condition here on the MCFGs means that the class of grammars, string languages, is exactly the same class of string language defined by tree adjoining grammars. So the string language defined by tree adjoining grammars is exactly the string languages defined by well-nested MCFGs at dimension 2. Okay, so these two approaches to learning mildly context-sensitive languages both require this well-nestedness assumption to work. And I don't know if that's coincidence or whether it's actually something deep at this point. But going back, this is so the basically result here is that exactly the same algorithm that we used before for learning PCFGs, for learning trees works here, except we need a slightly stronger condition for the anchoring, but everything else is exactly the same. Okay, that's kind of, so this is like something for the linguists, which I'll skip over. so I think tree adjoining grammars and MCFGs are not generally considered by linguists to be descriptively adequate. So they're not powerful enough to describe natural languages in the way that syntacticians want to describe natural languages, okay? But one way that is using what are called minimalist grammars, which we can view as a sort of lexicalized MCFGs with a particular feature calculus. And minimalist grammars were introduced by Ed Stabler kind of about 20 years ago, and they've had a lot of impact in the sort of mathematical linguistic community. So, the basic issue here is that, like, when we sort of zone out a little bit, we sort of just like abstract away from all the technical detail that I've been presenting here, okay? And view a minimalist grammar, think about what the non-terminals of an MCFG are. There, you can view them as a states of a bottom-up tree automaton that recognizes the derivation tree, okay? Now, non-terminals, the way we think about them, you know, in a context-free grammar is traditionally as just an atomic symbol, okay? But in an anchored context-free grammar, PCFG, they're not an atomic symbol anymore. They're really a pair of a word and the distributional vector of that word. And in an MCFG, then they want a set of pairs of strings, and then some vector over these contexts that that represents its distributional properties. And so the real question is, is there any way of getting between these two views, right? So one view where we're taking the sort of formalism that syntacticians think is necessary to describe natural language syntax, and this sort of perspective where we're sort of thinking about the representations that might be learnable using these sorts of techniques. Is there any way we can kind of bridge this gap? I mean, one might be eliminativist about this and just say, well, actually, we don't need to worry about what the syntacticians think because they're wrong. But I think they're probably right, partially right. But yeah, so I'll talk for long enough, I think, already. So taking points here, I think, is that you can learn large classes of phrase structure grammars probabilistically. And these grammars can be defined by explicit structural constraints, so anchoring, these monotonicity constraints and so on. And you can learn them just from strings in a computation efficient, strong probabilistic model. And then, so the scientific claims then are that early acquisition of syntax is driven by distributional learning. And then this very big picture one, which is that class of possible human grammars is identifiable from strings, which has some kind of meta-theoretical things, but I'll stop there. Anyway, thank you for your attention. Fire away any questions if you haven't asked them already.
Yeah, thank you. This was really interesting. So, yeah, my question is really just like, what are the things that are missing in order to make this scalable on the actual raw data? So, one thing I could imagine is the size of the grammar may be an issue, if I'm not wrong, because the number of non-terminals is strongly related to the vocabulary size.
I think that's not. I mean, I think that's just at a certain point. That's just a modeling assumption. You adjust the size of the non-terminals to. So from a theoretical. Let me just go back. Yeah. So in the PCFG case, in the realizable assumptions, the non-terminals, the terminals, the distributions of all words is going to lie in a subspace, which the dimension is the number of non-terminals of the grammar. Okay. In reality, that's just kind of a model, that's just a tunable hyperparameter. You say, I want to have a gram which has 100 non-terminals, a gram which has 10 non-terminals, and you just kind of find the best low dimensional approximation you can of that. I think the major issue is that this relies on independence assumptions that are kind of false because of semantic constraints. So when we define this, so this is the quantity that's difficult to estimate, right? You can estimate this using kind of this is kind of the posterior probability of a kind of predicting U versus V in a particular context. Okay, so if you have some a masked language model, if you have some deep learning model which has a masked language model objective, you can kind of more or less read this off from that just by kind of trying a whole bunch of different contexts, and you can estimate this kind of. If you do that, what you find is that even words that are supposedly completely unambiguous, right? So say you take two words that are both unambiguous nouns, right? Say assumption and skirt, right? If you plug this into that, you're going to find a huge difference in the probabilities, because the sentences in which you can occur find assumption and and skirt and toothbrush, they all may be unambiguous nouns, right? But there's a huge probabilistic dependency on the rest of the sentence that isn't factored through that non-terminal category. Okay, so there are sort of two things you need to do, I think. One is either you consider a version of the corpus where you replace it with some sort of fine-grained syntactic tags or whatever. You do some clustering first, or some attempt to remove the semantic dependencies, okay? Or you have some kind of ancillary variable where you have a dependency on something which represents the semantics of the sentence. So you can then kind of factor out the distortions that you get in here. You kind of want to factor this into two things, one of which represents the semantic factors and one which represents the syntactic factors, if you want to recover a syntactic tree. So that's why I quite like this compound PCFG work that your colleagues at DeepMind did, that Chris did. That I think is really because there you have this kind of additional parameter, which is kind of as a semantic parameter, and then once you've removed the dependency on the overall meaning of the sentence, then the syntactic dependencies then come to the fore more. Or at least that's how I read that paper. Yeah, I mean, apart from that, it's not. I mean, it's not particularly kind of computationally demanding. And the experiments I was doing would cost about like $1 per instance. So on Amazon, so it's kind of it's not very computation intensive.
And just to be sure, so this expectation of U, so you sum over all the left and right, so basically over all the context, but is it only over the context that appeared in the corpora, or is it all possible contexts that could be generated by the grammar?
Yeah, so here this is just a normalization factor. So what I did with the empirical work was, rather than using all of the contexts, rather than using full sentence context, I just used kind of the adjacent words and used the kind of word clustering algorithm to get so basically projecting this infinite dimensional space into a kind of finite low dimensional partition. I think I've got some. Okay, let me just. Yeah, so I mean, so what I did was I just clustered the words based on the local distributional context using not Brown clustering, but similar sorts of things. And then you just use that to get a low dimensional approximation to the to this infinite dimensional thing. And then that expectation is just the normalization factor that you use to make everything add up to 1.